how I started. That was many years ago, and it was in a different place. I came from the Soviet Union here. Oh God, it was in 1978. But before that, I was always interested in language, and I'm horrible with computers, and I really didn't like to write code because to me, it sounded very unintuitive. And so many years ago, we're really talking about 50 years ago, I started thinking about giving machines the ability to communicate with us in a better way than writing this code, which in my time it was octal code, which you can imagine how hard it is. Most of us may not even know what it is. In order to say plus, you would say something like in octal code 0, 1, 2 or something, and then there would be the first operand, second operand, and a third one. Well, it was quite hard to do. And so one of the first projects that I did was to teach a machine to understand one of those algebra word problems, like 5th or 6th grade. Car goes from city A to city B, a train goes from city B to city A, they meet somewhere, and so on. And so the machine was supposed to read this text as text, understand what the issue was, and then solve the problem. And I was very happy when I successfully was able to parse and solve a whole textbook of such problems in algebra. So then I got very excited, and I'm also interested in poetry, and I decided it's time to teach machines to produce something exciting for people, and I taught it to write poetry. It was in Russian, unfortunately for you, because you cannot really see it and read it, but to me it was a truly a remarkable experience. It was, there was like one printer on the whole lab, and the way the system worked, you would come in there and give a bunch of cards to an operator with your code. The card came from a different office. You would write the code on a piece of paper, then an operator in one room would put this text into punch cards, and then I will bring the punch cards and bring it to another room and give it to operator, and then let me come on Wednesday and we will run your program and show you the results. So that was the debugging cycle. And of course, nothing worked, and I got back this huge output, and I had to figure out what's going on. And then the issue was that there was like one little hole, extra hole, a missing hole in the octal code, which I need to, take some glue and so you don't understand how lucky you are that you don't need to deal with these issues, but that also, I guess, made me feel, kept me on my toes, because I really need to write code that didn't break. And so eventually I debugged the program, and the first time I saw this wonderful poetry generated at like 3 a.m. in some random machine room, it was a truly remarkable experience. Well, anyway, so eventually I decided to come to this country, and I was lucky. The first office I walked in was at CSL here, and I got a job, and I'm there since. So Cambridge is the only city in the US I lived in, and MIT is the only place I worked in. So, but I'm lucky that I found them. And I started working on, also continued working in language. Some of the things we did over the years, we built a question answering system which we called START, which was by far the first question answering system on the web. Some of the ideas from START were eventually used and implemented by IBM people. I worked with them quite closely to build the Watson system that won in Jeopardy. A little bit later on, we had a project with Nokia, and we put a START system, sort of not quite on the phone, but working over internet, and we built a question answering system that you could ask the phone certain questions and ask it to perform certain procedures on the phone, and that was before smartphones existed, of course, and it was on a vanilla Nokia phone. It was a total magic that it worked. We went to Helsinki several times. I talked to senior vice presidents, and I said, look, it's very interesting, and you may have an edge over your competition. Did something disappear here? Yeah. Oh, I see it. This is a piece of. Okay.
It's a great story. We don't want to miss it. Thanks.
Yeah, I actually wonder what I could show you. Let me see if I can do that. So it looked to me that it was an important system, and I tried to convince them to put it on the phone, but they just wanted to make sure that the system actually sits on the phone. Unfortunately, the word cloud did not exist, so I had a hard time explaining to them that everything does not need to be on the same gadget, and we could go through internet and get answers this way. But I was never able to convince them, so we let me actually show you the system. All right, so again, it's hard for you to imagine the world without Siri and without smartphones, but imagine a phone that does nothing but making phone calls. So there's no audio except for some music, but you need to read the. So these are some of my students who act as if they need to go on a trip, and that is, yeah, it tells you about Startmobile, which how we call the system. So this is, he would type the questions. Later on, we connected it to speech, and he wasn't sure he needed to take the code, so he asked about the weather. Again, now it's sort of silly. Every phone has weather, but again, it's a different world. That was in 2006. So. It was our system. We just made a film about describing our system. Yeah. Yeah, commercial is not the right word, but something like that. Yeah. So you recognize the train station. He arrived in Cambridge, and he is totally lost. And so he asked, "Where am I?" And this is pretty much the month the first GPS came out. So we connected the phone with GPS. He showed him the map. Now he knows what he is doing. Well, this is a different, you may recognize that there was a beautiful lawn, but now they build these buildings here, so it dates a little bit the film. Again, it was 2006, 2005, 2006, yeah. Okay, this is a side thing. He's trying to reach his mother to tell her something, but she's not answering. He's a bit desperate. So we're able to figure out actions on somebody else's phone. So he types in, "Remind my mother to take her medicine at 3 p.m. and we will get back to that story later." Well, this is the data center. He likes the Frank Gehry architecture, I guess. And he wants to take a picture. Take a high-resolution picture using flash in 10 seconds. It's remarkable that even now, almost 20 years later, they cannot do these things. It's totally ridiculous. Right. Well, he wants to talk to this guy. So again, these are my students. And he's a little bit bored, I guess. He wants to play music or video, so he doesn't know how. So he asks, "How do I use the radio on my phone?" And the machine tells him, gives him some directions about how to do it. Again, today also you cannot ask your phone how to do things, unfortunately. Certainly not in English. Now he knows. They turned out to be very good actors, actually. All right, now it's his mother. who is a research scientist in my group, and so he got now the warning, the alert got inserted on her phone, and they were scheduled for future, so it happened at 2 p.m. or whatever he said, or 3 p.m. Take medicine at 3 p.m., and so she remembers. He meets his friend. And this is one last story. He's going back, he gets into a car. Again, imagine a world without Google Maps, without anything. And so we were able to, there was something called MapQuest. So we connected together several things. So the question was, how do I get from here to Federica's house? So you need to understand what here is, you need GPS. Federica's house you get from contacts in your phone, and then you send this information to MapQuest that gives you directions. Well, anyway, so this is the story. So we build a system. Yeah, this is just right. So we built a system and we gave them demos and all that. And then they kept asking me about putting Start on their phone, finding a chip, have a compiler for Lisp on the Nokia phone. And then, like several months later, there is this news that there is new phone that Apple came up with, iPhone. So very exciting, does stuff much more than that Nokia phone. So I come back to this senior vice president, tell him, look, there's this new baby on the block. They're doing stuff, and eventually they will catch up with us, and you need to really start doing something about Startmobile. He says, do you know how many phones Apple sold? I said, well, I read in the Times that last month they sold about, they were quite expensive though, they sold about 1,000 or several thousand units, so I tell him that. He looks at me and starts laughing hysterically. He said, we, Nokia, ship 1 million phones every day. Why do we care about Apple? So famous last words, right? So what happened was I guess we stopped worrying about them. We published a paper describing the system with all the examples. That was in 2007, I believe, in October or September in California. And then somebody was sitting in the room, and 2 months later, a little company named Siri got started in California, and a couple of years later, they sold their stuff to Apple, and the rest is history. So this, again, I'm not telling the story to show off about Startmobile, but you will, some of you will become professors, so you'll be entrepreneurial, maybe or not, or some of you will go to industry. That it's important for you to know that the company that seems big today may not be big tomorrow. Like Nokia was almost sold on a yard sale to Microsoft several years ago, and their mistake certainly contributed to that. And you need to find people to work for, or maybe start companies with people who have this vision that the world is changing all the time, and you need to be on your toes. So that's really the only message there. Well, anyway, so back to what I have been doing. So we did all these things. There was we were sort of the first to come up with an idea of that to answer questions on the web, it's not enough to look at the text of all available text for you. You really need to do some pre-analysis of the text and create some structured information, and it will make it much easier for you to answer these questions. And one of my students, in fact, the one who played the visitor, after he graduated, he went to Google. And you may know that Google has these 20% days, where one day of the week, at least at the time, you're allowed to work on anything you want, assuming you get a go-ahead from your boss. And then eventually you share it with the company, and if they like it, they pick it up. And so he worked with us on this idea. We had the system Omnibase, which sort of could be viewed as a pre-digested web put into a database. And he built something much bigger on a Google scale, which they at the time they called Google Squared, and then renamed it to Google something, some net or something. And about, I don't know, 18 years ago, they totally switched the search based on that. So now if you ask them questions, it used to be that they will give you just hits. Now, if they have the answers in the structured form, they will immediately on top give you a very precise answer, which again is due to some of the stuff that we did. All right, then, so that was language, and then a few of us, about 8 or so years ago, started thinking about the future of AI, and wrote this proposal to the National Science Foundation, which we called Brains, Minds, and Machines, where we told them that we don't believe that the problem of intelligence could ever be solved by one discipline, with computer scientists or cognitive scientists, neuroscientists, and we really need to work together to do that. We also said that we don't believe that we need to look at one modality, whether it's language or vision or robotics, that again, we should go across modalities. In fact, I believe that it was a big mistake made by AI many years ago, that people totally separated. Language people have no idea what vision people do. Vision people have some of their applications working with robotics, but they don't understand what they do. And it's a mistake not only because people can learn from each other, but it's a mistake because, in fact, they made the problem harder. Just think about a baby in a crib. I have to yet see parents who put an encyclopedia or a dictionary into baby's crib and say, go learn. What happens is the baby observes the world with its vision, touches the world with its hands, tactile information, and hears first parents and then friends talk about things, and puts all this quite often redundant information together, and this is how learning happens. So the learning of recognizing objects and recognizing language and recognizing what you it happens at the same time. And this is easier because you have redundant information that confirms what you're learning. But currently, what most language people do, they train and train and train on language data until they build a decent parser. What vision people do, they train and train and train on billions of images until they get decent object recognition performance and so forth. And I don't believe that they will succeed dramatically well if they continue doing that. We need to put things together. Well, anyway, so going from language, so we were lucky. We got grant, got accepted, got a sizable amount of support from the government, and that allowed me and other people in this building and across the street to hire totally awesome people in different fields. And so now, at least my group is interested not only in language and question answering, but in vision and robotics, and especially in putting things together and how children learn language and how children understand what other people think and so forth. So these are the types of projects we're working on. So I could very quickly, well, I can answer any of your questions if I can, of course, any time. I'll give you in a second. But then I have a few slides about some of the things we did very recently. It's not really a technical talk, but it's has to do with the current state of machine vision, and I could show you the slides, but go ahead with your question.
More about like your proposal, trying to combine language people and vision people. What does that practically mean? Like, you can't do vision without language. Like at an like experimental or scientific level, what does it mean to combine both disciplines to kind of advance both ways of doing the research? So like, how do you incorporate one with the other?
Well, you co-train. In fact, we have, yeah. So at least this is one idea. I'm not saying that we have all the ideas and change that we have to try very hard to get. Yeah, that's right. And we do have, in fact, I can show you a couple of recent papers where we try to do exactly that.
Co-training.
Anybody interested in machine vision here? Okay. All right. So let me see if I can find those slides. How many of you know what ImageNet is? Well, okay, most people. All right. So I think if you ask most people, both in this building and across the street, and I think ask you as well, I think we all believe that much progress has been made in AI in the last, say, 8 or so years, and especially machine vision. Indeed, if you read papers, or especially media, you will see that there are these claims that machine performance on ImageNet, it's again, for those couple of you who did not raise their hands, it's a data set of images. At this point, I have like 20 million of those, which most object recognition systems train on and test on. So on that data set, the performance is claimed to be 97%. And an earlier paper of a couple of years ago claimed that human performance on object recognition on ImageNet is 94%. So what does it mean? Does it mean that you're wasting your time here? We should all go home. The problem is solved. Maybe, but if you ask people, I don't know if you had these experiences, who actually use these detectors, who allegedly have 97% performance, you will know that they never work out of the box, and even if you train them, it's certainly not even close to that number. In addition, even number 94 is also a little bit silly, because if 6% of the time you would not recognize objects on the street, I'm a little bit worried about your safety if that was the case. So we need to explain this disconnect, and maybe before we do that, we need to sort of understand, again, these numbers have to do with object recognition, understand what is it that needs to happen to recognize a visual scene like this. So of course, we need to recognize objects and categorize them, understand what class they belong to. But in addition, we need to understand spatial and temporal relationship between objects. We need to be able to recognize events, not only objects, what activity is happening there. We quite often need to predict what happened a second after that frame in the video or that image, or 5 seconds after that, or explain what happened before the event that you're observing. I see mostly upper torsos of all of you here, but I pretty much can guess that there are some legs somewhere there as well, even though I don't see it. So you should be able to hallucinate, fill out the gaps of what you don't see. And of course, humans are totally wonderful of all of these tasks. But if you look at machines, it's true there had been some good progress made in object recognition and object categorization, but all these other human abilities that are required to understanding the scene are not there yet, not even close in our machines. So the question is, why is this the case? And some people say, oh, well, visual understanding requires knowledge about the world, which is a claim which we will agree with, and that our human visual system is tuned, and some even say biased, to process structures which are typically found in the world and to recognize objects and events that make sense to us as humans. to maybe explain a little bit more about what is meant by that, I'll show you a quick video which got blurred on purpose. Yeah, I don't know, it's a bit too bright here. Do you see what's going on here? Right, so, say it again?
No, I think it's fine.
You could see it. Can somebody tell me what they saw?
It seems like he picked up a phone.
Yeah.
It's kind of big, so that's just an observation. And then he put it down, put his headphones on,
Right.
and then move the mouse, which
Okay.
kind of moves differently. too,
Well,
but-
which is perfect. And why is it that you were able to do it? Because you only saw just really a couple of pixels on the screen, but you sort of know that you pretty much understood, oh, this seems to be a sort of office situation. What happens in offices, that something looks like a computer, something looks like a human. So you hallucinated the rest, and you were able to give me a perfect answer. But of course, it's also true that if someone confronted with the fact that you were wrong or shown something which is different than usual, you will not collapse and say, I have no idea what's going on, God help me, but you will actually recover, dismiss your biases. I call them biases because you're sort of biased to and you will be able to recognize this unusual situation. So let me show you the actual video, which is unblurred. So there are at least, 5 things here which are totally crazy. First of all, the phone was a shoe. The headphones were some Coke or beer cans. The mouse was a stapler. There is also, I don't know if you see that, a trash can instead of an old-fashioned desktop, and a toaster for what used to, again, looks like an old-fashioned disk drive or something. So you were able to quickly dismiss your biases, and humans are very flexible about that. But the question is, can machines do that? And before we answer this question, we need to understand what the data sets that you all know, the modern sort of religion, the machine learning stuff, they require data sets and all that. So is it possible that our data sets are biased? If you ask people how these data sets are collected, for example, ImageNet, they will tell you, oh, well, they're collected at random from various photo sharing sites. And because it's at random, that means that they're not biased, they're random. Well, let's look at a little bit more careful how they. So it's true that they collected at random, but what is Flickr? I don't know if any of you, I don't use it, but I assume some of you upload stuff on Flickr. You don't upload random pictures of random positions. I call it this best photos effect. So you select the ones that you like. Usually those pictures have predictable backgrounds. They're correlated with objects very nicely. If it's somebody on the beach, in the back is the sea or sand, or a plane is in the sky, or at worst on a runway, frying pans are in the kitchen, and so forth. And so they're all more or less, because you want them to be nice, these photos, they appear in preferential positions. And there is also almost no occlusion, because if you don't see your objects, why would you even upload it and share it with the world? And even the angle from which you take that is not random, you want to make sure it is. So as a result, our data sets are actually biased. And there is this famous adage in AI that your models are as good as your data sets. So what happens, current networks, the winners of all these competitions in ImageNet, are extremely good at exploiting these biases in the data sets. And as a result, they overperform on ImageNet, on data set that they're trained on, and they very badly underperform on the real world. And so the problem that we want to, so I asked a question before, can our machine overcome biases? So we first need to see whether we can debias the data set collection process, our data sets. And we believe we have the answer, that the answer is yes, and we actually spent several years working on it. We just sent a paper to NeurIPS describing it. So it's a platform which we called ObjectNet. You ask a question?
Yeah, I have a question about the term bias, because I mean, in a certain way, can't I make the argument that, okay, but my experiences are biased as well? Because I mean, I only see objects from a certain angle from my perspective.
Yeah.
A street, most of the time I see it during the day. I don't see images from the bottom of the ocean. So in a certain way, my
you are
experiences
absolutely right, but
also
this is exactly why I showed you that video.
Yeah.
That when you saw the unblurred video, you didn't say, I've never seen a man putting Coke cans on his head, therefore I have no idea what I see. You immediately saw what you saw. You immediately saw that he put chances are you have never seen somebody taking a shoe and putting it, but did you have a problem recognizing it? Well, but our machines do. And this is exactly why we say it. It's true that most of the time, 99, whatever it is, percent of time you look at objects, they're in this perfect position, but do you see what this is? You know it's a bottle, right? I don't want to but there will be no problem. And we can, if you want to have robots in our house helping us and seeing objects that they need to see to help us, we cannot tell them that everything is in the right position, because if they don't see, if all of a sudden we do this or we put the food all over the place, the robot will be totally stuck. We really need, our networks need to be able to generalize to different positions, and currently they don't. And I will show you some numbers explaining what I mean. But that is a good question. Yeah, thank you. Right, so this is our, yeah.
On that note, since you said something about assisting, maybe the lesser able to assist, and then being able to recognize things as important, is that a big part of the impact that you hope to have, or?
Yeah, our goal is not to say that whenever they say 97%, it's in fact a much lower number. Our goal is to convince, right now, fewer and fewer people work on object recognition, because if it's 97%, why would you waste your PhDs on making it 97.5%? But we want to tell the world that the problem is still there with us. And of course, the main goal is to, after that, to create better detectors, to not to understand how machine vision works, but I also firmly believe that we need to do it at the same time with understanding how human vision works, and do these things together, and hopefully there will be this wonderful virtuous loop between understanding humans and machines to build better gadgets eventually. So that's the goal, yes. That was supposed to be the end of last sentence of my talk, but all right. So this is what we do. We don't believe in random, because the web is not random, the Flickr is not random, and so we have to do it the hard way. We have to actually create every image from scratch. Thank God there is this Amazon Mechanical Turk. I assume you all guys know what it is, right? And so just requires a little bit of money. And so we give them tasks. So we I have a researcher in my group who one day went to his home and made a list of all the objects he has in his house. We threw out some of them for reasons I will explain later, which are like with this food, it's hard to put upside down. And so we ended up with 324 different types of objects. And we put in a list, and we ask many thousands of Turks to take randomly one of those 300 objects, to put them randomly we will tell the coin toss happens on our side. We tell them, take a bottle, bring it to the kitchen, rotate it at so many degrees, and I'll explain how this is done because we cannot give them numbers, and put the camera from the top or something. So we took some additional steps to make sure that there's as little bias as possible in the collection process. So in particular, they are not showing any instances of any object classes. We didn't want to bias them that this particular bottle so that they will all go to buy a particular bottle. We just use English and to describe objects. And as I said, right now it's English, but it could be any language potentially. And it's we don't do it in more than 3-4 words. Usually it's 1 actually. And they're guided in their work. So they download an app on their cell phone, and that app allows them to use some animation which allows to tell them what exactly they need to image and how. And you will see this in the next video, a little rectangular prism that they need to align with the physical object before taking the picture. So here are the instructions. Right. So he on the phone. On the right is what he sees on the phone. He is told which objects to take, where to move it, and here's this prism that he aligns with the object. It needs to be exactly inside the box. The prism, in this case, knows where the opt and front is. In other cases of other objects, are different things. And so now he's told to rotate it, and again align it with the prism, and take a picture, and then press a button and upload it. So this is what the Turks do, and this is a somewhat more schematic description of what they do. So it says here, collecting natural data, controlling for biases. So the controls are object class, which again, one of those 324, whatever it is, classes. Occlusion has a word soon on top of it. We don't do occlusion yet. This is work in progress. And then object orientation, we have about 50 angles, which again, using that prism, we don't tell them move the object 48 degrees. We move the prism 48 degrees so that he needs to align it with the box. And then camera orientation and background, whatever rooms we tell them to bring it to. And so that all this random sampling sort of gets generated as a task to the Turk. He takes an image, or she takes an image, and then other Turkers make sure that that was the right label for that image, and that it has the right background, and so forth. We have a very sophisticated verification process, and eventually, when we throw out something that we don't like, after we get a data set. So here's what we have so far, and we're still collecting as we speak. As I said, we have 324 object classes. What will be important for the next couple of slides, that we made sure that many of those classes overlap with ObjectNet, with ImageNet, because we want to make sure we can compare how systems perform. So it turned out to be 116 classes. So we collected about 70,000 images, and about 4,000 people were involved. Sadly, which resulted in the waste of a lot of money, after validation, only 40,000 were retained. And here are some of the reasons of why we threw out so many. Now we know better, and we will be much more careful about that, but it was a learning process. So here are some of the examples. So we removed 43% of the data. Well, 10% was just silly because people had some. We will ask them to take a picture of a phone or of a bottle, and they will put it on top of their desk with a check, and so we could see the check numbers, and so we had to. It was just foolish. We had to throw out this information. Another 10% had to do in some countries. In this case, I believe it was India. Some entrepreneurial people realized that Turks could make them some money, and some of these people don't even have computers or cell phones to do any work, so they hire a bunch of people, place them all in one office, and tell them to bid on jobs from Amazon Turk. As a result, it totally defeated our purpose. We wanted to have as much variety in the background and in objects, and all of a sudden we started seeing that same object in the same background of the same office. So now we wrote some code that we will unfortunately not allow these people to participate, because we don't want those same images from them. And 23%, which is a large number, and that is the hardest for us to deal with later in the future. So they didn't have an orange or banana or something, and so they will go to Google, search for that object, and then take a picture of a picture and send it to us. And even, of course, the instructions told them not to do it, but so in any case, so we had to throw quite a few of those out, and if we find a cute way to automatically recognize that it's a picture of a picture, we will not be able to, we will be able to do it in a much more efficient way. Well, and anyway, and so this is just a test set. Yeah, go ahead.
Did a lot of the costs come from maintenance of the Amazon Turk you were saying?
Of the cost? Well, the cost, each time they take a picture, we need to pay them. And you know, it's, we want to pay them decent so that per hour they don't make less than like $10, $15. And so this is the cost, yeah. And it's what we also believe is important, so that people don't overtrain like they do currently on ImageNet, that we spend a lot of effort to make everything automatic. So at this point, all we need is a check, and then we can press the button, and another 50,000 images will be collected. And this way, people will not overtrain on those same objects, even in our data set. If you're interested, here are some of the objects. It's about half of objects in our data set. And some of them are in italics, and those are intersecting with ImageNet. Mm-hmm.
Yeah, I have a question. So, if I make the argument that like the power to generalize, like generalization in general, occurs from having a large volume of previous experience. So the more previous experience I have, the better I can generalize. The more I have seen objects in different contexts, the better is my ability to sort of recognize that object in a novel context and sort of put it in a frame. Now, 40,000 images sounds like really a lot, but if I really compare that to the human experience, I would say that's maybe 3 days of our lives.
Yeah, you missed something that I said like a minute ago. I said this is just a test set. We will not allow anyone to train on this collection. If they want to train on 20 million images of ImageNet, or 200 million images, or billion images, this is their problem. This is the new experience that I want those networks to experience, and to be able to generalize to, rather than train on. I absolutely agree with you. Although, to be fair, a baby does not see 1 billion images. Yeah. And so there is something there that allows us to very quickly generalize.
Have there been studies that sort of try to find a relationship between number of images and certainly object recognition? So have there been any studies been done that?
For machines, yes,
Yeah.
but for humans, these studies make no sense, because look, you take a 4-year-old, and I have grandchildren now, so, and you buy, have a birthday, you buy them a little toy tractor. They've never seen a tractor. You tell them, well, this is a tractor, so they play, go back. Then the spring comes or the summer comes, you take them to a farm. There is this huge thing, different color, different parts, totally different, and he says tractor. One example, one-shot learning. So we need to figure out how this is done. This is what needs to happen. Yeah.
I'm really interested in crowdsourcing approaches to research, and I'm sure you've heard of Sebastian Sung and iWire.
Yeah.
And I don't think that required any monetary incentives. So what sorts of differences do you think there were between yours and something like that? Because it's just available online, I think. Like, why couldn't you put the app in like the Play Store or the Apple Store and just have people buy it? I mean, use it there.
Leave what there. What the images? What I don't know quite understand what you're saying.
I'm
Sorry.
really interested in crowdsourcing approaches to research.
Yeah.
So I'm wondering what differences there were between something like iWire from Sung and yours that required like monetary incentive, or what sorts of differences there were, or how you came to the conclusion that you should provide monetary incentive.
Well, first of all, yeah, I think it's nice people make effort. I don't think we need to worry about. And we are a rich country. We have funds, and I see nothing wrong in helping people with their livelihoods. It's sort of a totally side economic issue. But I also yeah, possibly we could tell people, look, we have the school project, help us solve the vision problem. Or possibly we will be able to get it for free. But I don't. You know, there are some research issues. You could try to have a bunch of people solve a math problem, but it's not that interesting to take a shoe and put it on top of you know, a table or a desk. So I think people made an effort. I don't see anything wrong in paying them. Well, anyway, so here are some images from ImageNet. So you see, in this case, these are chairs. Well, you see what I mean by stereotypical positions and stereotypical backgrounds. And here are those same class chairs in our dataset in ObjectNet. Well, you see how they differ by rotation, by background, and by viewpoint. And this is what we are striving for, to get as much variety so our future systems can learn to generalize better. Some other example with this prism. This is a chair on its side. And again, none of you have any difficulty recognizing that. Some bottle on a chair. She's a transparent bottle, which again is also very important for us to be able to recognize. A knife on a sink. Again, it's a different background, but we all see that knife very nicely. A shoe on somebody's kitchen counter or something. It's also upside down, but we all see that this is a shoe. None of the networks is able to do that. All right, so that's if Mandan asked me to show you one slide, that would be the slide I'll show you. So here is it 3 parts. So this is the top one. Top one means that the network is allowed to only one guess. There is also a top 5 where a good answer is supposed to be found when you guessed. You have 5 guesses and one of them matches the target. But I don't want to confuse you and show these other curves. This is the green. Everybody sees that. So it goes. So we took 5 winning those years object detectors, starting from AlexNet in 2012, VGG 1914, ResNet 15215, DenseNet in 16, and NASNet in 17. And this is, you see how the performance improved from about 50% to about 85 or so percent on top one. And this is trained in all 1,000 classes of ImageNet. The next curve is to do the same thing, except to look at their performance on the intersecting classes. The instances of those the images are still from ImageNet, but only from 116 classes that that intersect with ours data set. And you see the performance goes down by about 10%, mostly because some of the images in ImageNet were very easy for ImageNet, and since we only looked at things that happen in our houses, they didn't have cats and dogs, and so this now goes from 40 in 2012 to what is it, about 70 in 2017. So the next I will show you, and again, the blue line is the performance on 116 object classes taking from ImageNet. So the next curve will be performance of those same systems on those same 116 classes, where instances come from our data set from ObjectNet. So what is your guess? Where would that next curve will be? It will go down. What's the guess? How much?
20%.
How much?
20%.
Dang.
So this is pretty dramatic. So these wonderful, you were still in maybe high school when AlexNet came about. There was this incredible publicity. So they do 5% on our data set. It's totally crazy. So this is, and this is what the community needs to see, and people need to understand that as good as these networks are, whether they're deep or shallow or whatever the current adjective is, they are not good enough to solve the problem. So that is the message. If you want to see some examples of what the networks did, I could show you that too. So going back to chairs, so here is what ResNet 152 said about this image. Here is top 5. So first choice was a vacuum cleaner, then it says is a cello, then a banister, a shopping basket, and a microphone. And after looking at some of those, I actually became a bit more optimistic about the state of the world. There are some reasons for all 5 of those, if you think about it. It's just that systems are stupid, and just looking at this little curve, they say, oh, it's a cello or something. So if you guys could figure out a way to combine the smartness with generalize it with not look locally at this little thing and declare it a cello or a banister, or because of the angles say that it's a vacuum cleaner or a shopping basket, because this is how you care. It's actually remarkable how but of course none of you will ever say that it's a cello, right? And then some other similar examples. This is for chairs. And for other objects, we told them to put an iron, I guess, in the bathroom, and somebody cleverly put it in the sink. And of course, the best networks in the world says it's a soap dispenser because it's in the sink. It recognized the background, and it was good enough for it. So again, you're the future. Please figure out a way to build better systems. And another cute thing, wash bashing and. Binder was an iPod for some reason. And I need to finish up here. So this is just to show you. It's not readable, but I will blow it up in a minute. This shows you how NASNet performs differently, almost 90% on certain object classes and 0% on others. And if you blow it up, you will see which one those are. So this is the top end, and this is bottom end. I looked at it a little bit. I don't see any irregularities there, except for somewhat more symmetric objects are easier because if you rotate them, they don't change. So you see some of them on top. So that's the only thing that I noticed, but otherwise looks somewhat random. Well, anyway, so let's get back to our adage. So current approaches are truly awesome at understanding correlations and irregularities, and we do want them, but we don't want to only have that. And ObjectNet is a new test set that controls for all these things, for rotations, viewpoints, and backgrounds, and, which we hope will spur the field into thinking harder about how to build better gadgets. Of course, we want to do many more things. We want to understand exactly when and how they fail, rather than say number 45%. The main thing is we don't want to have this crazy disconnect between 97% somewhere, and when you actually go in the field, you get 40%. We want to make sure that performance on the data set is predictive of performance on the real world, and we know what it is. I talked about robots, autonomous cars. If autonomous car sees something upside down on the road, you don't want it to think something crazy. So it's important. We want to add occlusion. We have some interesting ideas of how to do it. Going to humans, we want to use short presentation time experiments to characterize when and how humans fail, because humans are not perfect on that either. And which properties of objects of the scene affect accuracy. And of course, this is responding to your question, we want to use all this understanding to develop better detectors and hope we'll do something interesting. So this is what I had to say. If you have any more questions, go ahead.
Yes.
Yep.
Absolutely. And first of all, thank you so much for coming. I know the presentation isn't over, but you have already taught me so much, and I'm sure everyone here appreciates your knowledge and wisdom. So I'm curious in discussing what Parsa, this gentleman, had mentioned earlier about, and also what you had talked about, how maybe young children prefer what seems like one-shot learning. So they see a toy truck, and then a few weeks later they see a real truck and they can recognize it. Something I've been learning a bit about recently is wake-sleep algorithms. And I guess the idea is, people, when during the day you experience things and then you go to sleep, and something is happening in your brain while you're sleeping, and we really think sleep is very important for learning, and so just like a crazy idea, I'm not sure if it's crazy, but just what I was thinking is, what if when we sleep, if we experience this toy truck, what if when we sleep we start creating our own variations of the truck, so maybe we imagine a truck with different properties, or larger.
That is quite possible, but in fact it may not even happen in sleep. In fact, it's a bit unfair to say that this is how humans learn, because I said it's a 4-year-old. That 4-year-old had 4 years worth of something. As I said, I have grandchildren, so I'm observing them. You give them a new gadget, and they kept they looking, turning it, throwing it, picking up, throwing it, picking up, trying to, and so maybe what they're doing is they actually try to understand. In fact, Podger had a couple of papers with his group on the subject, that they understand invariances to rotation and other types of invariances by just playing with the subject constantly. So what I said was a one-shot learning came in fact on top of 4 years of understanding that if you do this, it's the same object. If you do this, it's the same object, and that will make the problem much harder. So so in a sense, they do have either through just playing for many hours or various sort of hallucinations, whether awake or in sleep. It's quite possible that, but I don't know what it is. Yeah, go ahead.
I'm wondering what the implementation chain might be for something like this, because I guess if I wanted to try to have a machine recognize something, I try to reduce something like a laptop or a plate to a few wires, and then every time the machine would see the object, it would rotate and flip, and do all sorts of things with the wires until it matched up to whatever it was seeing. So I'm wondering what you implement at like 30,000 feet, since I'm not too, I don't know too much about machine vision myself.
Yeah, well, again, right, as you may have noticed, vision is new in my world. Right now, we looked at a bunch of existing networks. We have some ideas on improving algorithms. But what I didn't talk much about, I just mentioned it in the bullet here, that we in fact do plan to look closely, and not only how humans do that, but we plan to work with animals, which is much easier to study. If you study monkeys, then you can actually wire them and see what happens, and then you could, again, hopefully have this virtuous loop between understanding a little bit about ventral stream or various processes in the brain, and go back to the networks and use this information about humans or animals to improve the networks. So this is what I think that the future should be, at least could be.
And then for any human studies and any machine studies or animal studies, will you use like a minimum object, like the minimal representation that it could have, up to the most complicated version of it?
Yeah, well, we haven't made the decision. With humans, we can do anything we want, but we cannot get into the brain, unfortunately. Although, even that is not quite true. I don't know if you have a minute to describe that. We have access to mostly teenagers at one of the hospitals in Boston who have uncurable cases of epilepsy that do not are not helped by chemicals, by typical drugs, so they require surgery. And what happens in this case, they are brought into the hospital, they cut their skull, and they insert electrodes to the areas that the surgeon suspects where the surgery needs to happen, and then they observe them for several days, trying to pinpoint exactly where the future surgery needs to happen. And while they're wired, we we ask permission, their parents and them, they're sort of bored anyway if they're sitting there for 4 days doing nothing. So we show them movies, and we're planning to show them also things that will be maybe less exciting to them, to show some, show some images, show some language strings, and have them hear some language, so that we could try to see what happens in the brain when they see things, when they hear things, and when they see a conversation. And that will hopefully again help us to get understanding. But the images that you're talking about, whether they're minimal or get more complicated, we are certainly open to that. We could try to see what works and see if what is more productive and what helps. Yeah.
I had a question in regards to how a computer would learn, so the actual process of acquiring that object recognition. So when a human learns a language, for example, they're constantly associating an object with the name. So that is an association process. However, as they're learning the language, they learn the certain rules and begin to say, all right, this is sit. The present tense for the action to sit is to sit. However, as they learn on, they associate sit, the past tense, with sat. There's like a time of overgeneralization.
Right.
So for example, like to hit, they would do hat instead of the correct version.
Or hit it or something, most likely, yeah. Most likely hit it, because this is here.
My question to you is there a way to implement the forgetting or since humans have the ability to ungeneralize something, to make it more specific, to have that fluctuation of specificity. Oh my
goodness. Thank you. That's specific.
Specificity.
Thank you. Okay, you know what I mean.
Right.
Do you think that is that possible to implement in computers? The fluctuation between these two?
Yeah, I think it is, but it's of course, but we need to start with actually being able to generalize, which is already a hard problem. Overgeneralization is true. Kids show that it's known that many papers showing it in language understanding. I'm not sure whether that is happening in object recognition. But for language, of course, you said that they learn object. I actually think things happen at the same time. I think the grammar and the lexicon, and plus, of course, object recognition are all happening at the same time. Because they very rarely, mother or father will say, it's a spoon, or just say spoon. Child constantly from very early age hears full English sentences. Some, depending on the family, parents more or less speak down to the baby, talk down to the baby a little bit, but when they talk to each other, they talk normal language. So this is a constant input that the baby hears, and therefore that needs to happen at the same time. Because if you never hear spoon, if you never hear table, how would you usually say put the spoon on the table, and the child needs to understand. It's a sentence, it's a structure, and eventually tenses, and eventually object that participant, constituents of that structure, and that is a total miracle, and we pretty much have no idea how that works. As I said, there is some work more recently, and we also had some papers on the subject, but this is still hypothesis, and they don't even come close to how amazingly quickly children acquire language. So again, a lot for you to do. Yeah.
So I know you were saying like our networks are only good as our data set. So do you think like the way to overcome this problem is just on the data set side? Like if ObjectNet was 20 million and you trained the networks that exist now, do you think they would be able to have higher performance, or are the networks that exist not capable of recognizing?
Yeah, I don't think which sort of repeats your question. I don't think it's in the issue is the numbers. I really think we need new ideas. There is this long curve that goes down of unusual things. You will never be able to have as many objects to predict every possible angle that I could have this bottle on, or every possible background that you have never encountered before. As you saw in these examples, you have absolutely no trouble seeing things you have never seen before. And our machines don't have this ability. I don't think it's just training. We really need to find clever ideas of generalization, or eventual forgetting, or specific. Now I have trouble with this word myself, but okay, go ahead.
Yeah, I have another question that is sort of related to Alana's. So I have not a computer science background, and it's hard for me to understand how the computer approaches the task. So, I mean, if a child has not seen anything before, the way I would approach it subjectively, I would say, okay, it's a vehicle, it has 4 wheels, it's big, so it's most likely used in agriculture. That's how I would guess about an object that I have never seen before. So sort of schema learning or associative learning, sort of trying to rely on previous experiences. How is the algorithm of the computer even try to guess?
Well, what happened was 20, 30, 40 years ago, people would come up with sort of semantic ways to figure out how image recognition, for example, could work. But more recently, there was this amazing success in machine learning techniques that it was very hard to argue with success. And all they need is a bunch of instances. This is a spoon. Have a million spoons and different backgrounds, and then a million cats, and a million dogs, and a million tables, and then this is the training set, after which the system, as you saw with what is cello or something, was able to very quickly, what they thought was generalization, to figure out, oh, I saw something like this before, and it looks like what I saw before, and this is a cello. There is no what we think is sort of semantic understanding. We don't know what humans do. We have some kind of a networks in our brain as well, and some people might say there's no difference, except all these networks that currently the winners of the competition, modern machine, they all feed forward, which means that they sort of learn from low-level stuff or high-level stuff and never come back. Whereas actually it is known that in our brain there are many more wires that go back, which are not used in current architectures, but that's we don't know how that works. So the modern technologies are based on numbers, on number of training examples, and they're never given even parts mostly these days. They just it just works, especially if you see the numbers 97, they say forget. And the same is happening with language. People are trying to do parsing, this or that. Now everything is done in raw numbers, and it is more robust than previous approaches, but it reached a plateau, and people now want to come back and say, well, let's have some way hybrid systems, some rule-based systems and some statistical-based systems, and hopefully the hybrid will work better.
So when you say that we need to approach it in a different way so that the models are more generalizable, do you refer to changing kind of the way that neural networks are like implemented, or do you think that maybe there needs to be an entire new kind of model?
The answer is yes. My guess is that all of the above. It's hard to predict what we don't know, but to me it sounds like the current technology is just not powerful enough to capture all the variety that, especially to deal with to even come close to what humans could do, and therefore some new ideas are needed. Yeah, it is likely that some of the old ideas will stay, but I think we would need to augment them with many more new ideas which we haven't discovered yet.
Hi, has this ever been attempted prior with a different approach, or has the standard attempt always been educating through images? Has there ever been a different approach to accomplishing your end goal, what you're doing now?
To vision?
Yes, for vision.
Yeah, as I said, there were people were saying the approaches that had to do, this is the type of object, humans have a head and two hands.
So they've always, from the beginning, associated with images, they've never tried a different approach?
Well, they were associated with images, but they were trying to be a little bit more semantic and rule-based. But if you want to recognize images, what do you mean by a different approach? You have to, yeah.
Just out of curiosity.
Yeah.
So, going back to the graph that you had, so one of the major trends with that, if you look at ImageNet's progression, is one of the biggest trends is that you have a higher parameter count in terms of connections between all of the layers. And so for instance, ResNet 152 is 60.2 million parameters.
Right.
So parameters to everyone else is basically the value that you multiply inputs from one layer to go to the next layer. So there's a general trend that with neural nets being universal function approximaters, as you increase parameter count, presumably they can do better on any given task. From what I recall, based on the graph, there was an overall 45% decrease in accuracy, but as you increase the number of parameters, they were still able to become more accurate. So
yeah, it's actually I believe it is the where is that slide? It is interesting because it could have been much worse.
Oh right, yeah.
It could have been, in fact. Where's the next one?
I think
right. It could have been that this curve is flat.
Right, and so what I was
in fact I thought that it will be,
right.
But that means that the progress is actually being made, which is very, I think, optimistic for the whole field, and but we are just nowhere where we want to be. Right. But it looks like these ideas help. Whether they help course, we wanted to worked very hard to debias our data set, but it will never be totally debiased. So a pessimistic view of this is, yeah, well, but your data set is still debiased, and therefore these machines just became better.
Well, so like coming from so the labs that I work in back at UCF, I work with Dr. Shah, Mubarak Shah. I don't know if you know him. Basically, it's all like supervised learning, semi-supervised learning,
right.
All computer vision dealing with object detection and recognition. Right. And so like the general trend is just like if we make the networks bigger, they do better. Like that's the general correlation with the field. Right. So I guess, and so like one of the other things as well with a lot of machine vision is this idea of transfer learning, where let's take something that's trained on ImageNet and apply it to some new data set, because it has a bunch of really good feature detectors already built in because of the variety of ImageNet. So then, would that necessarily be like, I guess what I'm kind of like struggling to wrangle, at least internally, is that it is like it's possible that what we're seeing with ImageNet is that it's not actually producing good feature detectors, which I think is kind of like what your argument gets towards, is that the feature detectors, so the kernels within the networks, they're not able to operate at a level that allows them to generalize well. Is that correct? Or?
Well, let's back off a little bit. First of all, as much as it's fun to build gadgets, we, at least many of us, are in fact are interested in how things actually happen here.
Right, of course. Yeah.
So, second, I believe all these high numbers, whether they have to do with 97% on object recognition or 90% on parsing or part of speech, I think they all had to do with the fact that we humans are very predictable. So here's a silly comparison. Like with my children, I text a lot, and so at this point I almost don't type. It pretty much knows what I'm saying. So you can have an article in New York Times saying the T9, whatever the thing is called, that predicts your next word, is a system that overperforms humans. It knows what I'm about to say, which is totally stupid, of course. But people are very predictable. Therefore, these very clever networks are capable of latching on. They just count words, numbers, symbols, whatever it is, and they know what will happen next. But it has nothing to do with intelligence.
Right. Of course.
So the performance itself, I don't think tells us anything about how things are actually happening or teaches us anything. So while it's nice to be number one on something and write the next paper, I do think that at least some of us should be interested in how is it done.
So that was a fundamental disagreement I had with my PI at UCF, was the fact that that's what I cared about. He cared about performance.
Right.
But the point that I'm getting at is, I guess, in part, should we be trying to give them such, like, in a way, domain-specific tasks where it's like discern the objects in an image as opposed to something that's more complex, which is potentially something like scene labeling, where it has to learn to actually do the classification and then wrangle.
Oh, absolutely. We certainly believe that, in fact, some of the work in our group is to come up with these tasks that people have not considered before, which exercises the networks and the systems. And yeah, absolutely. I think, Chris tells me that I should stop. Yeah.